Hello everyone, let's continue our discussion on pin placement. So before looking into the concept of pin placement, let's take an example circuit. Okay, so we are planning to implement a small circuitry, a small handful of gates. This is one of the sections of that particular circuit. Okay, so for example, we have flip-flop 1, one of the sequential cells, we have flip-flop 2, and we have the input ports as D in 1 and the clock port as clock 1 and the output port as D out 1. Okay, similarly there is one more section. Let's say we have this particular section. It again has a flip-flop 1, flip-flop 2, but of a different color, and this flip-flop 1 is been driven by the input port D in 2 and the clock port clock 2, and the output port is basically D out 2. Okay, so this set of the circuit is driven by clock 1 port. This set of the circuit is being driven by clock 2 port. Okay, along with that we have some pre-placed cells as well. So we have done the placement of some IPs in the previous section. So these are those pre-placed cells. So we have this block A, okay, and the block has got some connectivity like this. So it receives its input from D in 1, from the D in 1 port. It receives its and second input from D in 2, okay, and the output goes to one of the inputs of the combinational gates. This is just a circuitry to explain the concept of the placement and routing. Okay, so we have this pre-placed cell which has got connectivity something like this, and we have another pre-placed cell, let's say block B, which receives its input from clock 1 and clock 2 and provides a clock output, and this is the clock output port. So currently now we have four input ports, which is D in 1, clock 1, D in 2 and clock 2, and we have three output ports, D out 1, D out 2 and clock out. Okay, so this is a sample circuitry for the design that we are planning to implement. Okay, and let's say there is one more section of that particular same design. So this section has got flip-flop 1, flip-flop 2, but of a different color, and this flip-flop 1 is being driven by D in 3, which is the input port, and this particular flip-flop 1 is again given clock 1. Okay, and this flip-flop 2 has got an output port which is D out 3, but the clock port for this particular flip-flop 2 is clock 2. So this kind of circuitry will be very good example to help understand the timing analysis for interclocks. So interclocks, by interclocks we means that the two flip-flops are being driven by different clocks. So this is driven by clock 1, this is driven by clock 2. So that's basically the concept of interclock timing, and we'll be talking about that in the further videos. So this particular example will be helpful to understand those timing concepts. Okay, let's take one more section of the same circuitry. So we have this flip-flop 1, flip-flop 2, but of a different color. The input port is D in 4, the input clock port is clock 2. This flip-flop 1 is driven by clock 2, this flip-flop 2 is driven by clock 1, and we have the output port D out 4. So now we again have some set of input and output ports. We have D in 3, D in 4 as two new input ports. Clock 1 and clock 2 already had been defined in the previous slide, so we need not consider them over here. And we have two more output ports, which is D out 3 and D out 4. Okay, let's take one more pre-placed cell somewhere in the center. So we have this pre-placed cell block C, which gets its input from D in 3 and D in 4, and the output of this particular pre-placed cell goes to some combinational logic, let's say this particular NAND gate and this particular NAND gate. Okay, so now let's look into the complete design. We have taken this particular design. So it looks something like this. This is the first section of the design, this is second section of the design, and this becomes your complete design. So let's make the connectivity first of all, a proper connectivity for this particular design. So for example, clock 1 is coming twice over here, clock 1 is coming over here and coming over here. So let's pull this and put it over here. So we'll take the clock 1 we'll take the clock 1 information from this clock 1 port. We'll take the clock 2 information from this clock 2 port, and similarly clock 2 and clock 1 will do the same thing. Okay, we just tie it up to the respective clock 2 port, and we tie this to the respective clock 1 port. Okay, so all these things, the netlist connectivity and everything, basically what goes to what, this connectivity is being defined in a separate tool. It's called in a separate language. It's called VHDL or Verilog language, and this particular connectivity of gates is refers to a netlist. So this is what a netlist means. It basically refers to the connectivity of different gates, the connectivity information between different gates. Okay, so now we have this set of input ports, D in 1, D in 2, D in 3, D in 4. We have two clock ports, clock 1, clock 2. we have four output data ports, which is dout1, dout2, dout3 and dout4, and we have one clock output word, which is clock out. So let's try to place all of them in the chip that we are trying to design. So we have this particular core and die, and there is an area between the core and die which is empty. Let's try to fill this up with the pin information. So generally the trend is we put all the input ports on the left hand side and all the output ports on the right hand side, but it might vary from designer to designer or from design to design. So some might prefer to put input ports at the top and output ports are at the bottom. Some might prefer to put input ports in the left and top and the output ports on the bottom and right. Okay, in this particular circuitry we'll take an example where we put all the input ports on the left hand side and we put all the output ports on the right hand side. Okay, so let's do that. So we have this particular input ports D in 1, D in 4, clock 1, clock 2, D in 2, D in 3, and the output ports are placed over here. So there are two things that has to be observed over here. First of all, the ordering of the of the input ports are random. D in 1 comes first, then D in 4, then D in 2, then D in 3, and the ordering of the output ports are again random. So it's D out, D out 1, D out 3, D out 2, D out 4. And the reason is pretty simple. It's basically depends upon where we are planning to place the cells. Now for example, block A, if we refer to block A, it was been driven by D in 1 and D in 2. So we try to place it close to D in 1 and D in 2. Similarly, block B has got direct connectivity to clock out 2. So this could have been placed somewhere over here, but that would have required some additional decoupling capacitors. So we plan to place it over here, and we'll put some buffers for this particular block B to come out to clock out. Okay, and for example, there are again some cells which will be placed over here, which that refers to D in 2, and as a result of that the D in 2 is being placed over here. So there are multiple reasons, and we have, and also what we have tried to do is, for example, we know that now we have a cell, we have a block which is placed over here. We have block A, block B and block C. So no cells can be placed in this area, no flip-flops can be placed in this area. So we have made sure that all the input ports, which is D in 1, D in 4, D in 2 and D in 3 are out of this particular way, are out of this particular area. So basically a complete knowledge of the design or of the functionality of the design is very important to understand the pin placement. So this basically creates an handshaking between the front end and the back end team. The front end team is the one who defines the netlist connectivity that we just talked in the previous slides, and the back end team has to decide the pin placement. So this is where the handshaking comes into picture. Okay, and the second thing to observe is the clock ports, which is clock 1, clock 2 and clock out has the clock ports are bigger in size compared to the data ports. Okay, and that the reason for this one is the clock is the port which is driving all the cells continuously. The clock 1 and clock 2 continuously send signal to the flip-flops, all the flip-flops in the design. So basically these are the one that drives the complete chip, or drive the flops in the complete chip. So we need the least resistance path for the clock 1 and clock 2, and bigger the size, lower is the resistance. Similarly for clock out and clock out over here as well. So we need the clock port, we need the clock signal to move out of the chip as fast as possible, because it is being driven continuously. So we need the least resistance path for the clocks, and that's what we have done. We have created bigger boxes for clock 1, clock 2 and clock out, so to make sure these are very least resistance path. So once we are done with the pin placement, the next step is to make sure none of the automated placement and routing tool doesn't place any cells in this particular area. This particular area should be blocked for the placement and routing tool. So that's what we do. We do a logical cell placement blockage. We block this particular area using some blockage, and this makes sure that the automated placement and routing tool doesn't places cells in this particular area, because this area is reserved for the pin locations. Okay, so finally when we have the logical cell placement blockage, our floor plan is ready for placement and routing step. Okay, so now we are done with the floor planning step, and the next step is to move into the placement and routing. So what we'll do is, since I'm already running out of time, and this is the end, this is the final lecture of this particular section, and from next section or the next video onwards we'll move into the further concept of placement and routing. Okay, so let's try to begin placement and routing steps from the next videos. Thank you.